This video is the third of a three-part series discussing the fundamental theorem of calculus. In the first video, we discussed the mean value theorem of integrals. In the second video, we discussed and proved the fundamental theorem of calculus part 1. In this final video, we will discuss the fundamental theorem of calculus part 2, prove it, and then do some examples. This is based on the OpenStax Calculus book, Volume 1, Section 5.3. The fundamental theorem of calculus part 2 is in fact the fun part. Finally, we get to the part that you use on a daily basis. In the center of the screen, you'll see in the blue box the statement of the fundamental theorem of calculus part 2. Again, our condition is that the function be continuous over the closed interval from a to b, and uppercase letter f of x is any antiderivative of the function f of x. In that case, then we can say that the definite integral over f of x from a to b is the difference in the antiderivative function evaluated at the upper limit of integration b minus the antiderivative function evaluated at the lower limit of integration a. Note the relationship between the two. Remember that if uppercase letter f of x is an antiderivative of the function f of x, then the derivative of the antiderivative gives us back the function. This means then that if we undo the derivative on the lowercase function, this should give us the antiderivative evaluated at the upper and lower limits and subtracted. Let's prove the fundamental theorem of calculus part 2. Recall from the fundamental theorem of calculus part 1 in the second video that we proved that the area function, uppercase letter a of x, is one of the antiderivative functions of the function over the closed interval from a to b. If we then let uppercase letter f of x represent any antiderivative of the same function over the same interval, then we know that both this antiderivative function, uppercase letter f, and the area function must be in the same family of functions. Because they're in the same family of functions, that means that they differ only by a constant. Since all the antiderivatives in that function are vertical translations of one another, up or down by a constant, this implies that we could write any of the antiderivatives, uppercase letter f, as the area function plus some unknown constant represented by the letter c. Now we can write, since we know that the area function is equal to the definite integral from a to an unknown variable x of the function with respect to t, and because we know that the area function at a, which represents no area at all, since I started at x equal a and stopped at x equal a, this implies that that would give me 0. Because these two things are true, this means that I can write the antiderivative function, the unknown one, represented by the uppercase letter f, as capital F of b minus capital F of a. Now, since this has to be the area function plus a constant, I can plug in the b and substitute it into the area function plus the constant. Then I can substitute the value of a into the area function plus the constant as well. Distributing the negative will give me a c minus c. Since I know that the area function evaluated only from a to a is 0, this reduces to becoming the area function at letter b. This is represented by the definite integral of the area from a to b of the function f of x. This proves that this formula for finding the value of the area under the function f can be done by taking any antiderivative function and plugging the upper limit and lower limit of integration into the antiderivative and subtracting them. Note that the order must be upper limit minus lower limit. In general, when we do this, we write this notation of the difference between the two limits of integration substituted into the antiderivative function with a long vertical bar after the antiderivative with the a and b, the limits of integration, written on it as they are written on the integral symbol itself. Let's take a look at what this might mean. Since any antiderivative will work, then we typically would choose the one where the constant is already 0, just for convenience sake. Even if we don't, the constants will cancel out just as they did up here. In that case, then, it makes sense to choose the one where the constants are already 0, so we don't have to mess with something that's going away anyway. Let's take a look at several examples. In this particular example, we want to evaluate the area under the function 2x plus 5 between the values x equals 0 and x equals 4. You know from the previous section that you could graph this and use a geometric formula to find it. Now, however, we're going to use what we learned in Chapter 4 about antiderivatives and what we've just learned about the Fundamental Theorem of Calculus Part 2 to put them together and solve this without having to graph it. Let's first find some antiderivative function of the integrand 2x plus 5. To do that, I'll split the definite integral into two pieces. The integral from 0 to 4 of 2x dx plus the integral from 0 to 4 of 5 dx. Remember that an antiderivative for 2x applies using the power rule for integrals. We increase the power by 1 from 1 to 2, and then we divide by the new power, which is 2. We can accomplish the same thing for the constant, remembering that the constant 5 actually represents 5x to the 0 power. Increasing the power by 1 will make it x to the first. Then we divide by the new power 1. In this case, this is an antiderivative of the original integral, 2x plus 5. We're going to choose the constant to be 0. We want to evaluate this between 0 and 4, so we'll put a long vertical bar with a 0 at the bottom and a 4 at the top. This means I need to plug in those values into the antiderivative function. We plug in the upper limit first. I'm going to simplify my antiderivative first and write it as x squared plus 5x. This will make the algebra simpler. In the next step, I can go ahead and plug in the upper limit, which will give me 4 squared plus 5 times 4. Now I need to plug in the lower limit and subtract that entire value from the value of the upper limit of integration plugged in to the antiderivative. When I put 0 in and square it and add 5 times 0, of course I get still 0 for this lower limit of integration. I still need to evaluate the upper limits, which gives me 16 plus 20, which ends up being 36. That means that the area under the function 2x plus 5 between x equals 0 and x equals 4 is 36 square units. Let's now look at example 2, which involves trig functions. I can do a similar thing and split the integral, since it's the integral of a sum, into the sum of the separate integrals. Notice that the limits of integration stay the same, as does the differential. In this case, I'll get the integral with the same limits of integration of sine of x dx, plus the integral with the same limits of integration of cosine of x dx. Now I need to evaluate these by finding some antiderivative function. An antiderivative of sine is a function that when I took the derivative of it, I got sine. So the derivative that I would have taken would have produced sine. The antiderivative of sine is negative cosine of x. The antiderivative of cosine is sine of x. I need to evaluate each of these between negative pi over 4 and 7 pi over 4. Remember that these are both multiples of pi over 4, meaning they're multiples of 45 degrees. The location of both angles is in quadrant 4. Since if I do 7 pi over 4, I count around the circle 1, 2, 3, 4, 5, 6, 7, ending up in quadrant 4. And if I do negative pi over 4, I start and go backwards by 1. In fact, these represent the same locations. Let's see what happens when we plug them into our antiderivative. In this case, I might put the negative outside and then compute the cosine of 7 pi over 4. Then I need to add in the sine of 7 pi over 4. Finally, I need to subtract from all of this the lower limit of integration plugged in, which would be minus the cosine of a negative pi over 4 plus the sine of a negative pi over 4. When I evaluate this, what will I get for an answer? Recall that on the unit circle, multiples of pi over 4 produce the same values for both sine and cosine, which are positive and negative square root of 2 over 2, or 1 divided by the square root of 2. Since I'm in quadrant 4, the cosine, which represents x, will be positive. This, however, will stay negative because of the negative on the outside. That gives me negative square root of 2 over 2. Sine in quadrant 4 would be negative, which will also give me minus square root of 2 over 2. This accounts for the first two terms. The next minus is the one in front of the entire lower limit of integration plugged in. I tend to do mine in steps so that I don't make mistakes and I don't have to go back and correct. Thinking about this here, I know the cosine of negative pi over 4 is also in quadrant 4, so it gives me positive square root of 2 over 2, but the negative makes it negative square root of 2 over 2. I know that in quadrant 4, negative pi over 4 would be negative square root of 2 over 2. When I simplify what I have here, the 2 here have the same sign and a common denominator, so I can add them and get 2 square roots 2 over 2, negative, which reduces to negative the square root of 2. Inside the parentheses, the same thing happens. I have a common denominator of 2, they have the same sign, and adding gives me 2 square roots of 2 over 2, negative. That causes the 2's on the outside to cancel, and will give me instead negative the square root of 2. Now in this case, when I continue this problem, I have a double negative. The double negative is going to make it a plus. This would give me, finally, negative the square root of 2 plus the square root of 2, which gives me 0 for the final result. What must that mean about the original function? It must mean that when I add sine and cosine and restrict it to this closed interval, that half of the area is above the x-axis and half of the area is below the x-axis, because I got a net area of 0. Let's take a look now at the third example. In example 3, we're looking at the integral from 0 to 1 of x minus the square root of x. Looking at this problem, we can of course split it into two different integrals with the same limits of integration. This is the integral from 0 to 1 of x dx minus the integral from 0 to 1 of square root of x dx. However, we need to rewrite the square root of x in its power form, x to the 1/2. Now I can apply the power rule to each of the integrands to find one of the antiderivative functions. An antiderivative of x is x to the second power divided by 2. An antiderivative to x to the 1/2 is x to the 3/2 divided by 3/2 or times 2/3. Since this is a definite integral, I need to evaluate between 0 and 1. In the next step, I will want to plug in the upper limit of integration first and then the lower limit. In the first part, I get 1 squared divided by 2. Remember that dividing by a fraction 3/2 is the same as multiplying by the reciprocal 2/3. That then would give me 1 to the 3/2 power. Then I can do the subtraction of the lower limit of integration plugged into the antiderivative. However, the lower limit of integration is 0. When I plug it into these two parts, it should give me 0 in both cases. That means that I only need to think about the upper limit of integration. While this doesn't happen all the time, it does happen some of the time and is a shortcut to evaluating. 1 to any finite power is 1. This gives me 1/2 minus 2/3. Using common denominator of 6, I can write 3/6 minus 4/6 equals -1/6. What does this mean about the original function that served as the integrand? My original integrand, x minus square root of x, has a net area between 0 and 1 of -1/6. This must mean there is actually more area below the curve between 0 and 1 than there is above the curve. Let's now look at example 4. Example 4 involves the exponential function e to the x. We need to find just some antiderivative to e to the x. Fortunately for us, e to the x is its own antiderivative and its own derivative. That means that I can now write this as e to the x evaluated between 0 and natural log of 8. Once I have that written, I can simply plug in the upper limit and lower limit of integration to do the subtraction. This gives me e to the natural log of 8 minus e to the 0. When e and natural log are back to back with nothing in between, then I can simply go ahead and separate them and they undo each other and give me what was in the argument to natural log. In this case, 8. Since e to the 0 is 1, this gives me 8 minus 1, or 7. Now let's look at example 5. Find the average value of the function over the given interval. Our function is the cosine of x, and our closed interval is from -π/2 to +π/2. Remember that we can find the average value, represented by f bar, as 1 over b minus a times the integral from a to b of f of x dx. I see that my function is wonking in and out, so let me handwrite it for you. F of x is the cosine of x, and my closed interval is from -π/2 to π/2. In this case, I need to go ahead and compute b minus a. b minus a would be π/2 minus a -π/2, and the double negative makes it a plus, so that I end up with an interval that is pi wide. For the next part, I need to calculate the definite integral of f of x from a to b. This would be the integral from -π/2 to π/2 of the cosine of x dx. I need any antiderivative of cosine to do it. One of the antiderivatives of cosine is sine x. This is the one where the constant is 0. I'm going to take sine x and plug in the limits of integration. When I do this, remember that I always plug in the upper limit first and then the lower limit and subtract. This leads to the sine of π/2 minus the sine of a -π/2. Remember that on the unit circle, when you're looking for π/2, that's up here at the top between quadrants 1 and quadrants 2. Negative pi, on the other hand, is down here. Negative pi over 2 is at the bottom between quadrants 3 and quadrant 4. Now that I have this information, I know the sign of pi over 2 must be 1, since it's up here on the unit circle at 0, 1. Likewise, the sign of negative pi over 2 must be negative 1, since on the unit circle it's at 0, negative 1. The subtraction is part of the formula, and it's in between. That gives me a double negative, which gives me the final result that is 2. That, however, is just the area under the curve. How can I find the average value? Take that value and divide by the length of the integral, which was pi. This means that in the next step, I can now find that f bar, representing the average value, is the area divided by the length of the integral pi. This represents the average value of that function between negative pi over 2 and pi over 2. Let's take a look at one more example. This is also an average value problem. I can see that it's messing up a little bit, so let me write down the function for you. This is the function e to the x over the closed interval from 0 to 2. If that is the interval that I have, how can I compute this? In order to find the average value of the function e to the x over the closed interval from 0 to 2, I simply need to evaluate that f bar is equal to 1 over the interval 2 minus 0, the length of the interval, times the definite integral from 0 to 2 of e to the x dx. Now the length of that integral from 0 to 2 is of course 2. This will give me a 1/2 at the front. Now I need an antiderivative to e to the x to finish the definite integral. An antiderivative to e to the x is e to the x. And now I will plug in the lower and upper limits of integration to find the value. This gives me that I've got 1/2 times, and I can put the rest of it in parentheses and evaluate e to the second minus e to the 0. This should give me the average value over that interval. Since I know that e to the 0 is equal to 1, then I can rewrite this in the form of 1/2 e squared minus 1/2. That is the average height of this function over that interval. What if I then wanted to find the value c between 0 and 2 where this function had that actual average height? In other words, could I now find c such that f of c was equal to 1/2 e squared minus 1/2. In order to do that, I would need to plug it into the original function, which is the exponential e to the x. That would give me e to the c equal to 1/2 e squared minus 1/2. The next step, of course, would be to take the natural log of both sides so that I could solve for c. To take the natural log, then I would apply it on both sides of the equation since it's a 1-to-1 function. This would give me the natural log of the difference, 1/2 e squared minus 1/2, and the natural log of e to the c. The natural log of e to the c is of course just c, which gives me the natural log of the quantity 1/2 e squared minus 1/2. I could, if I wanted to, write the 1/2 e squared minus 1/2 back in its factored form with the 1/2 on the outside. This might simplify it a little bit and allow me to separate it in some way. However, I'm not going to be able to get rid of the subtraction in the center, so there's no way that I can get the exponential in here and the natural log to undo one another. This is going to be an irrational number. If you plug this into your calculator, you will find that you get about 1.1614. That is definitely a value that is between 0 and 2 on that interval. If we took that value and plugged it in, we would find that the y value at that point is exactly this 1/2 e squared minus 1/2. This is the final example that we wanted to do from section 5.3, covering the Fundamental Theorem of Calculus, Part 2. In the next section, we'll talk a little bit more about the consequences of positive and negative area and how it relates to the velocity, acceleration, and position functions. This is the end of this video.